Okay, welcome back. So let's discuss the following problem. Okay, so the question 3. So we actually say kind of an application of Green theorem, basically. So let's see. So let's try to understand. So we have a curve like this. So this is our curve C here. Okay, in positive direction, oriented in positive direction, and it's basically bounds a certain square, as you see. Okay, and we are going to, try to compute this line integral over here for this vector field. Fine. Maybe the first observation is, the first observations you may have is the following, basically. Okay, first observation, actually the region R. So let me say maybe this region R, the interior. So let's R. So here the inside, let's say the R. Okay, R be the region. Okay, enclosed by C. Okay, so R is just the inside of this square. But the problem is R is not a regular region, but R is not a regular region. So actually we cannot use Green's theorem directly. So what does it mean? Actually, if you look at the vector field, this vector field, maybe we should write it down like this. So first component is something like this, right? And this is the second component, x squared y squared. Actually, those component functions, so f1 and f2, are not actually defined at the origin, right? So the origin is the is actually where problem occurs. So actually f1 and f2 are not defined at the origin. Okay, so origin is, it causes a problem. So actually we cannot use Green's theorem yet. Okay. So actually, to make use of Green's theorem, actually we need a regular region, right? Therefore, somehow in our case, we have to avoid this. The origin. Somehow we have to exclude the origin, right? So actually, the idea is actually introduce a new region, okay, R prime, let's say in R, in the region R, such that first property it should have is it must exclude the origin somehow, because the origin is a problem in this case. Now, and the second thing is, of course, it should be enclosed by a suitable boundary curve. Positively oriented, suitable boundary curve. Okay. Therefore, we need a kind of a region. So let's try to build such a region, if you like. So maybe we should start with this, the original picture. And okay. So actually, maybe something like this. So this is the original picture, remember? Oops. Okay. So let me introduce a new here, a kind of a curve like this. Okay, a new one. Okay. Maybe the color should be oops. Okay, the red one. Okay, so we have, okay, anyway, so we have a kind of a unit circle here. Okay, C0, but in negatively oriented. Okay, so we just introduce a kind of a new curve. So let C0 here, just the unit circle, right, be the unit circle. Of course it is inside R, right, clearly. So because of this, I mean, this is just a unit circle. Fine. And what else actually we can observe? Then we can define a new region. Define R prime to be the region, okay, to be the region actually enclosed by actually the region over here. I mean, you can easily see. So let me use this kind of color. So this will be our new region. Okay, this part. So this part will be R prime. Okay, this yellow part will be R prime, if you like. Okay, new region excluding the origin. Okay, and this is actually, if you look at carefully, I mean, this one enclosed by a curve which is denoted by C prime, and C prime is defined like this: C union C0. And clearly by construction, which is, I mean, positively oriented and smooth, simple, and closed curve. Okay, the union of two closed curves, basically. Okay, fine. So we have such a thing. Fine, but now actually we can use Green's theorem, right, for this region actually. But first observation, just observe that the second observation, if you compute del f2, the second component with respect to the first variable, if you compute it, you can easily see that this will be the result. So this is the resulting expression, will be something like this. And on the other hand, if you compute the partial derivative of the first component function with respect to second parameter, which is y, you will end up with the same expression. But the best part of this analysis is that this is true now for all xy in R prime. Okay, not the R. Remember, in the original region R, we have a problem, origin. But now, in this newly constructed region R prime, there is no problem, right? Due to the origin. So origin is basically excluded. Fine. So we have this observation, and actually R prime is a regular region, and here this is a regular region. I mean, this is a regular region. Here R prime is now regular. Now a regular region. Okay, fine. And now we can actually use what's the apply Green theorem. So just apply Green's theorem for the curve C prime. Okay, so let's apply. So we have this kind of line integral of a vector field. So a Green theorem tells us that, right, this part is exactly the Green theorem. Actually, you can pass the double integral on the region R prime here, because remember, this is just the boundary curve of R prime, right? And then actually this is just f2 partial derivative with respect to x minus f1 partial derivative with respect to y. Okay, in general we will use P and Q convention, but actually it is clear, right? So what we are doing here. So, but now because of the observation above, these are exactly the same thing. So this is just a 0 on R prime. Be careful, always R prime, new region. Otherwise, it's not true, because on R we cannot use green theorem, but on R prime, green theorem is available actually. Therefore, this is 0. Oh, okay, fine. So this is 0, but what does it tell us? Actually, but this is not the question, right? So the question is about the curve C, right? Remember, we really wish to understand this line integral over here, right? Remember, but now we actually computed something else, okay, this is a closed curve again, but something else related to the original curve. So what was the relation? Just on the other hand, we have on the other hand, we actually have the following relation actually because of the properties of line integral. So this is just okay, so what was it? So we have this, so this is just a 0, right? And the dr, but remember, this is just the union of two curves. Therefore, we have C, the original one, if you like. So this is again a closed curve. Remember, plus actually the one we introduced, right? The line integral. I mean, this is again a closed curve, if you like. Okay, so we have this observation. Maybe I should. Okay, fine. So we have this observation. So this part is 0 because of the just the line above, right, where C prime is defined like this. Therefore, we have this nice observation, and because of this observation, actually, since this is 0, actually, so clearly, the original integral we are looking for is just the minus of this line integral. But remember, since this is this is just a unit circle, but in a negative orientation, right? Remember, it's oriented negatively. Therefore, actually, if you consider this thing, remember the meaning of the notation, where minus C0 means exactly the same curve, but in a positive orientation, right? So now we have again a unit circle, right? This, but we have now a positive orientation. Maybe I should be clarify like this. So now we have positively oriented unit circle. Okay, so this is again, this is just the x squared plus y squared, which is 1. And fine, so therefore it's enough to compute. So our final touch is it is enough to compute this line integral, right? So let's compute. So this will be not that much hard because you can easily parameterize this. Just use direct computation. Direct computation with the parameterization, if you like, with the parameterization given like this. Just choose the obvious one. I mean the obvious parameterization. So you have a circle. Therefore, this is the parameterization is just, okay, cosine t, okay, y will be sine t, and that's also t runs from 0 to 2 pi. Okay, and therefore, so I mean, so let's compute. So this one, the r, so this is just, I mean, this is a positively oriented unit circle, right? Therefore, this is 0 to 2 pi. So what was it? So just let me write it down. F is just, okay, sine t times minus sine t dt, right? Divided by 1. So can you follow? So what was the F? So F, let me go back here. F is this. So when you substitute, instead of y, we have, oh, maybe I should I write it down? Oh, maybe, okay, maybe I should write it down at least. Just a second, okay, to avoid some confusions. So actually, this is y, x square plus y square dx, right? And what was it? Minus x square plus y square dy. Okay, so this is the question, right? Basically. So let's compute, right? So let's try to compute using this parameterization. So instead of y, we have sine t. Instead of dx, we have minus sine t dt. But, okay, x squared plus y squared is just 1. Okay, minus, okay, x is just cosine t. dy, dy is again cosine t dt, right? And divided by 1. Okay, and therefore this is just, okay, 0 to 2 pi minus dt, right? Because you have sine square, therefore the result is minus 2 pi. Okay, therefore because of this observation above, I mean due to this previous observation, which was this, okay, let me denote by star, then due to star the final result, so due to the observation star, we have the following. So this was the original integration, now it is just minus 2 pi. Okay, fine, actually. So this is it. I mean, this is how we use green theorem, even if we were not able to use green theorem in the first place. But again, we have some trick. Then by using this trick, so-called, I don't know, introducing a new region or whatever, then actually we can end up with a kind of a nice result, a nice application. Fine. Next one, next question. Okay, so we have again a curve bounding a region. Fine, and we are going to evaluate this ugly line integral. So let's see. So let's maybe try to observe. So let's try to observe what we have here. Maybe this is not that much good. Okay, so let's try to see. Okay, I'm sorry. Okay, fine. So let's I'm going to sketch by myself. Okay, so anyway, so we have a kind of a picture like this, and so let's try to sketch our curves. So y equals y squared is a picture like this. This is exactly x equals y squared, and at +1, therefore we have something like this. This is x equals 1 plus y squared. And what else? Okay, we have this, and I guess that. And there are some other parts, and we don't care that much. And this is exactly when xy equals 2, this is xy equals 3. And this is exactly our region R here, this is the region R, and this is the curve. Okay? Positively oriented, bound some region, and let me call that region R. And some clear maybe observations here, just C is smooth piecewise, maybe I should write it down, piecewise smooth, okay, and simple closed curve. Okay, fine, this is the first observation, and the C actually bounds a region R, which is actually a regular region, and you can easily see on which on which the vector field, so what was it? So our vector field is just, so let me write it down. So f is, okay, somehow we just write arrow here, but in general I'm going to omit. So this is the first component, right? So let me write it down. So this is the first component, and the second component is sine y cube 1/2 x cube. Okay, this is the second component. So let me denote first component function by p and denote the second one as q, function q. Okay, and clearly this vector field is smooth, so it defines everywhere. If you take the derivatives actually on this region, no problem, and everything looks great. And then actually we can use Green's theorem, right? Then actually, I mean, setup is ready. So you have a nice curve, you have a nice region, you have a nice vector field, and then why not we use Green theorem? So by Green's theorem, let's see what we have. So we have the following observation. Okay, this is our original p dx in our new notation, q dy. This is the line integral. Now if we apply Green theorem and we just change the language, and we actually now land in the world of double integrals, right? And this was the theory, so del p, del y, and we have an area element. But if you compute, you can easily see that q del x, so this is just okay, I have, so this should be 2, right? So we have something weird. Okay, fine. So we have x comes from here when you differentiate this thing with respect to y. Okay, so we have x minus 2y, right? But I have a plus sign, or okay, we have a plus. Okay, we have a minus and plus. Sorry. Okay, fine. So we have this. Now the question turns out to be the following question. So let's solve this double integral. But remember, so we have a weird region. Remember what was the trick? So this is a very, I mean, it's hard to parameterize, how to write down the area elements, how to determine, you know. Remember, we just using the slices method. We use horizontal slices, vertical slices. We try to locate the point at which slice hit the region, blah, blah, blah. But now again, it is hard to do this procedure. What was the trick? Trick is use change of coordinates. Okay, now use change of coordinates. Okay, because we have a very, I mean, hard region to apply elementary procedures. So let's choose, I mean, remember how to choose those things. Actually, this is almost visible. If you go back, I mean, it's almost clear. Just let this thing u, right? Therefore, this thing turns out to be in UV language. This turns out to be u. This turns out to be u equals 3. And here, actually, v can be choose like this. So just choose x minus y squared to be v. Therefore, this turns out to be v equals 0. And this turns out to be v equals 1. Okay? So in UV language, it is easy to translate everything. But remember, we should translate really, I mean, the everything. Therefore, remember, we need to compute the Jacobian. We need to translate the area element accordingly. So therefore, we have u, and so what was it? So x minus y squared. Okay, let's denote by v. Then let's see what we have. Then we get the following results. Basically, first we should write it down the area element, but remember, we need to maybe it's easy to compute this determinant first, right? This is just the determinant of, remember the matrix. Just differentiate u with respect to first variable and the second variable, and then differentiate v with respect to first variable and the second variable. And this is the Jacobian, right? So when you compute this, we have something like this. But remember, at the end of the day, we take the absolute value, right? And hence, the area element is as follows. So dA, so we need dA. So we need to understand how to express dA in terms of u and v. And remember, so this can be done by just looking at this this thing, right? Absolute value, and this turns out to be du dv. And actually, this is just the inverse of this matrix, inverse of this element, basically, this matrix, right? And the determinant of this is just 1, 2y squared. Actually, we have an absolute value. Actually, we don't need, because x, y's are in the first quadrant, if you look at carefully. Then we have this. Okay, fine. This will be, I mean, actually, we should write x and y in terms of uv, but we don't need to, because you will see in a second. And actually, the region becomes, R becomes, okay, in this new language, R is just a certain rectangle, right? Actually, this will be something like this. Remember, V runs from, V. Okay, fine, we don't need that part. And V from where to where? From V1 to, this is exactly V equals 0. And U from U, this. And this part is just this rectangle here is the new region, right? So this is exactly RUV in UV language. Then let's compute. Then we almost done. And so let's do the final computation. So compute the following. So what was it? So we have this double integral. Remember, 2y squared dy. Now everything will be written in the language of UV. But now we have this element, but the dA is just du dv divided by exactly the same term here. So these are cancel out each other. So what is it? This is just a simple double integral with integrand 1. What does it mean? This is just the area. So maybe I should write it down. RUV du dv, but this is just the area of RUV. This is just the area of this rectangle, which is 1. Okay, fine. So that's all. I mean, this is the result. You see, we start with the line integral problem, line integral of a vector field. So by using Green theorem, so we have a passage from line integral, and we actually land in the territory of the double integrals, basically. Then problem turns out to be a double integral problem. Then by using techniques that we learn in while dealing with double integrals, we use those techniques and we end up with this result. Okay, fine. Nice. Maybe it is a good place to stop, and then we will continue. Okay, thanks.